very much for this nice introduction and for this opportunity to share with you guys recent results produced by my research team. So today I'm going to be talking about mainly how theory, in general, computational chemistry helps experimentalists on a way to design and construct new building blocks for perspective materials. So the main part of my talk will be about polyaromatic and non-planar polyaromatic systems, which are usually called buckybowls or fullerene fragments. The main question, like, why buckybowls? Why not something else? Because nowadays we know that like a lithium battery area is filled by graphene-based materials. So in the case of buckybowls, we have two non-equivalent surfaces, exa and endo, with very distinct properties. And here on this slide, I've tried to outline like the areas nowadays highly popular, where the buckybowls are highly popular as perspective materials. So it goes from hydrogen storage, biochemistry, organic light emitters, to metal complexes, and even molecular tweezers. Okay, so the story actually of buckybowls started a long time ago, and especially highly reduced species. So the first report was published in back in 1994 by the group of Larry Scott from Boston College. In their experimental study, based on purely lithium NMR data, they concluded that buckybowls, namely corannulene, is the simplest prototypic molecule. In a solution in a highly reduced state, it doesn't want to stay alone and tends to form supramolecular aggregates. Again, based on these lithium NMR observations and experiments, they came up with a model that's presented here. And after this publication, so such a structure became a textbook example. You definitely can find this example in many organic and organometallic chemistry textbooks. But if you go further and even just qualitatively consider the electronic structure of these systems, especially when you add more electrons to them. So this type of arrangement or aggregation is good for packing of neutral corannulene molecules. But what happens if you add positively charged, highly positively charged lithium belt in between? So which one is better, like endo-endo or exa-endo or two exa sandwich-like aggregates? That's an open question. So when we started our calculations about the system, we decided to quantitatively estimate what's more stable, and we immediately revealed that actually this type of system, where you have, instead of 4 lithium centers in between, we have 5, and this system is more stable by approximately 21 kilocalories per mole. Just to give an impression how big this number is, we can only say that room temperature is about 25-30 kilocalories per mole, just like a rough estimation. So it means that under normal conditions, this supramolecular aggregate is much more stable than what's proposed by the group of Scott. So, and we asked our collaborators from State University of New York at Albany to test this idea and to try to crystallize, to get some structural data about this. And after some attempts, they were able to synthesize that and to crystallize that. And here I am presenting what they have obtained, and this is a crystal structure of that system that 100% agrees with what we predicted. Right. So what also is important about this system is if you look at that system from their potential batteries point of view. So we can recall that graphene-based materials, like lithium batteries we're using nowadays in almost every electronic devices, they have a theoretical limit, and this theoretical limit is a lithium per carbon ratio is equal to 1/6, and you can just that's fundamental, and you cannot overcome it, right? So you need to modify your system chemically. In this system, in this sandwich-like aggregates, the lithium per carbon ratio is equal to 1/5. Keep it in mind that in industry, people fighting for every percent. So here we have about 20% improvement of these potential materials, right? So because approximately, there is a correlation between how many lithium cations you have between layers and capacity of the battery you produce based on it, right? I understand that it's very oversimplified model, but still works pretty well. So the more lithium cations you have between layers, the more capacity you have. And in these molecules, we expect that materials based on that would show better capacity, significant improvement in that. And then we started investigating these systems theoretically. And the main question, can we make even more, can we place even more lithium cations in between these two layers? Because there is still one space that is unoccupied between two 5-membered rings. And we found that if we do step-by-step of lithium cations by larger alkali metals, at some point, we open the gap and lithium cation can go inside. So here I'm just showing the diagram for the most promising candidate, and the minimum number of larger alkali metals is 2, like it's presented here, like 2 potassium cations, and they work like a lifting gate to open the way for lithium cation to go inside. And if you look at these numbers, their activation energy is pretty insignificant, right? It's plus 1 kilocalories per mole. It's almost nothing. And there is a significant driving force. It's like plus 12 kilocalories per mole. So we would predict from our theoretical calculations that this way should be working. And again, we ask our collaborators to test whether it's possible. So, because we know that theory is good only in the case when we have an experimental support. Otherwise, it will stay pure theoretical games. Okay, and that's what they found in a crystal structure. So again, they were able to not only to synthesize these systems, but also to crystallize that. And that's the fragment of crystal structure. And it shows exactly the same structural motif like we predicted, right? With 2 potassium cations sitting to the sides, and that opened the way for lithium cations to get inside, which is now occupying the space between 2 5-membered rings. And this gap is just closed by another potassium cation just because of the size. Okay, of course, that's a new and very interesting systems. And we surprisingly found that once you add, like you replace lithium cations by potassium cations, the electronic structure of these sandwich-like aggregates stayed about the same, almost unchanged. That was a real surprise because geometrical changes are pretty significant, like distance between 2 layers getting larger by approximately 1 angstrom when you go from only lithium sandwich to like potassium, or even if you take larger alkali metals like rubidium and cesium. So the geometrical changes are significant. But electronic changes are pretty much the same. But then we calculated more sensitive parameters, such as Nmr Chemical Shift, because previously, as it was exemplified by the group of Larry Scott from Boston College, lithium Nmr Chemical Shift is a very sensitive and very useful tool. Once we calculated that, we immediately found something that made us really surprised. So the central lithium that sits at the heart of this supramolecular aggregate shows unprecedentedly high chemical shift of more than 25 ppm. If it's true, that would be a new record because highest previously known chemical shift was about minus 16 ppm. But that's exactly the case when you find something that tends to be a discovery or pretends to be a discovery. That's especially in the theory. That's exactly the time when you have to check, double check, and check it again, right? Because in 99% of the cases, when you see something that wants to be a discovery, it's probably the result of your mistake. That's why I put this picture. So all such a observation should be taken very critically. And again, we ask our collaborators to check whether it's true or it's some kind of like artificial thing from calculations. Surprisingly, they found exactly the same what we predicted. So here I've shown you the theoretical calculated chemical shift for both like lithium centers sitting between 6-membered rings and central lithium that show this unprecedentedly large chemical shift and experimental data. So you see we're staying pretty much within 1 or 2 ppms from experimental data. It clearly shows this high, this record chemical shift. So we were right in predicting that. So from application point of view, it gives experimentally the tool how to precisely control the formation of such supramolecular aggregates, which is highly important when you consider these molecules as the potential building blocks for lithium battery materials, right? This chemical shift is unique, stays away from any other peaks, And when you see that, you definitely have in your reaction mixture the target compound. If you don't see it, you don't have it, right? So that's, and lithium NMR is nothing, it's not something like, nowadays at least, something very unique or exclusive technique. It's pretty much routine nowadays and available in many research centers and universities. Okay, so of course, once we see something that tends to be a record, we definitely wanted to look inside and to understand why we have this chemical, so like unprecedentedly high chemical shift. And we calculated shielding tensor and immediately revealed that the main difference between lithium sitting at the border and lithium sitting at the center, that comes from paramagnetic sigma ZZ component of the shielding tensor. And if we go even in depth, so we will see that the main difference comes from the pi orbitals of balls, not from lithium itself. So that actually means that lithium center sits in an electronic cocoon of two coupled balls. First of all, it shows that these surfaces, these two polyaromatic species, coupled. And here I'm showing you orbitals that exemplifying this coupling. You see how strongly they couple. And of course, then we decided like, okay, if it's connected to the coupling between balls, can we play with that? Can we tune and this coupling? For these purposes, we consider the whole range of alkali metals from lithium to cesium. And we immediately found that there is a big correlation between the size of their alkali metal and chemical shift of the lithium center that sits inside of their sandwich-like aggregate. And it correlates with experimental data. Not for all, because not all that sandwiches were synthesized so far, but for those who were synthesized, we see absolutely clear correlation between calculated data and experimental observations. And of course, we see absolutely clear correlation with geometrical parameters. So it means that the value of chemical shift shown by this central lithium cation can be taken as a measure of coupling between balls. So just simply measuring the chemical shift, we can say how far these surfaces, polymeric surfaces, one from another, and many other things. Okay, and that's this orbital show the difference in coupling for like sodium derivative and cesium. So you see how the coupling is getting weaker because of the size of this alkali metal cation sitting between 6 member rings. Okay, then we move further and said like, okay, we know something about corannulene molecule. What if we take another prototypic fullerene fragment? It's called sumanene. The problem is with that molecule is only one, so it's not polyaromatic, right? It has 3 CH2 fragments shown here by arrows that break aromaticity or conjugation in this molecule. But at the same time, here we see like how it influences the electronic structure and 3-dimensional charge distribution in that system that clearly shows no conjugation and no delocalization. But we definitely know, like from organic chemistry, we know how to make it polyaromatic, right? It's the same story like cyclopentadiene. So how to make it aromatic cyclopentadienyl by just a simple deprotonation. If we do that in 3 steps, we will get completely delocalized system, right? Okay, can we use this completely delocalized system, tri-anionic species, to construct these sandwich-like aggregates? So we calculated that, we provided comprehensive theoretical investigation for such a species, and we found that theoretically it's possible. And what's even more important, so if it's possible, that will show even higher metal to carbon ratio than in corannulene alloys. So it makes them even more promising building blocks for new lithium batteries. Okay, we analyzed electronic structure of these systems before we asked our collaborators to test our ideas. So we found that no significant changes in charge distribution between corannulene and sumanene-based supramolecular aggregates. The same we can say about 3-dimensional charge distribution exemplified by molecular electrostatic potential in this picture. And then that was the time we asked our collaborators to check whether we are right or it's just only theoretical model. And that's what they found in the crystal structure, exactly what we predicted in our calculations. So nowadays, both prototypic molecules, corannulene and sumanene, show tendency to form the supramolecular aggregates with a large number of alkali metal cations sitting between two layers. Okay, then we move to another side of this story, and we started thinking about stabilization of tri-anionic species, because extended polyaromatic open shell systems with strongly delocalized and paired electrons, they're believed to be ideal blocks for spintronic devices. But there is a main fundamental problem. Such systems are really rare, and so far in the literature, only 3 are known. That's a fullerene-based 3-, decacycline 3-, and by asantrial 3-, which the latter one is not really polyaromatic, right? So our idea was, if it was stable for tetra-anionic species, can we stabilize tri-anionic species in the same type of supramolecular aggregates? But once you consider that, definitely the first question that shows up is, what is the ground state? You have two balls, two polyaromatic surfaces, each has one unpaired electron. There could be different possibilities. After our calculations, we concluded that most probably all electrons are unpaired, and the ground state should be triplet. And here I just showing where these unpaired electrons are localized, as exemplified by spin density. Okay, the next question again, we have seen that we can manipulate with the coupling between balls. In the case of tetra-anionic species, can we do the same here? We definitely see, as shown by spin density, we don't have a coupling between balls, like sharing electron density between two balls, but definitely we have magnetic coupling. Can we play with that by doing the same things, changing size of alkali metals? And here I just shown how these how spin density for all the systems look like. We definitely see no electron density sharing between two polyaromatic surfaces, but probably we do have, because we see some polarization, like in the case of lithium species, we see polarization of spin density. Does it have an influence on magnetic coupling between these two balls? And indeed, that's what we found. So here I've just shown the J coupling constant as a parameter we calculated as a measure of magnetic coupling. What we found is rather impressive. So first of all, when we consider the smallest lithium cation, we see two magnetic coupling. When you go to another side of the series and go to cesium, we see almost no coupling, right? Because it's too far away. And if we want to optimize antiferromagnetic coupling between two balls, rubidium would be the optimal, right? That's the case when we maximize our antiferromagnetic coupling between two balls. So we see how we can finally tune the magnetic coupling, which is a very sensitive parameter, right? Between two balls by simply changing alkali metals. That is very interesting and unusual. And of course, we compared that to an experiment that was done by our collaborators. And what we immediately found is an excellent agreement between experimental data and our calculated parameters, which is not really usual for such a sensitive parameter as a magnetic coupling, especially of this, the coupling is reasonably small. That's why we had to go to very high level calculations like a multi-reference perturbation theory of the second order, rather than just a simple broken symmetry DFT. It shows clear tendency, but maybe not providing a correct quantitative results. Okay, the next question that came up to us, came to our mind, was, what if we mix up open shell tri-anionic ball and closed shell tetra-anionic species? Because if we have this, if we make it possible, there are several questions that show up immediately, like, where's this unpaired electron? Is it localized on one ball? So we have clearly 3- and 4- balls. Is it delocalized over the sandwich? Or it's partially localized or delocalized with some degree of localization. Okay, we move to comprehensive spherical investigation. What we immediately find is, if we do fully relaxed geometry optimization that resulted in symmetric species, that shows symmetric distribution of spin density. It means that single unpaired electron, is completely delocalized over the whole sandwich. But if you break the symmetry by adding, for instance, by adding solvent, like the glyme, to this system, this electron becomes highly localized only on one side. And we asked our collaborators to test this experimentally, and they were able to crystallize that and to do some measurements. And we did a calculations for fragment of crystal structures, and we found interesting thing that if we take this crystal structure, so the electron density or spin density is localized purely on only on one ball. But by changing environment, we can play with it. We can move it to more localized or less localized structures. That's interesting because it shows that in such a supermolecular aggregates, this spin density or unpaired electrons is highly fluid thing. So by just organizing or constructing or designing specific environment, you can make it strongly localized or completely delocalized. That's very unusual, and that provides us, especially experimentally, with a tool how to construct building blocks, for instance, for spintronics, with specifically determined spin behavior. Okay, and then that's like the last part of my talk today. It's a little bit different from sandwich-like aggregates I just talked about. So that's about encapsulation, right? We all know that because it's related to the story of endohedral fullerene metal systems, right? When metal is sitting inside of their cage of the C60 or C70 fullerenes, and we know that experimentally it's really difficult to control this process of formation of this highly interesting species. And from the very beginning of their history, buckybowls were assumed to be used for such a metal encapsulations, like providing like a chemical way to get these endohedral fullerene species. Surprisingly, so this idea was around for more than 40 years, and surprisingly, it was found that it doesn't work so far. So everything what we know experimentally know about corannulene species, for instance, shows that metals always go to exosurface because exosurface is a little bit more negatively charged. So here I just provided examples for neutral species, for mono-anionic species, and for di-anionic species. It always goes to the exosurface, right? Tri-anionic and tetra-anionic species we just talked about, they tend to form sandwich-like aggregates that show exa-exa coordination mode. There is only one exception. That's a cesium. That goes to endo-surface of corannulene, to mono-anionic corannulene, because of the perfect match between the size of cesium plus and corannulene ball. So there is still no encapsulation, but at least it goes to the endo-surface. And we decided to take this as a starting point and try to develop the strategy of constructing the new system for which we can guarantee the encapsulation of the metal center between two balls. Okay, that's the strategy we developed. So first of all, the step number one, we just proposed a couple of steps. Step number one is just go for cesium cations because at least we know that it goes to endo-surface. Step two is no corannulene derivatives actually, because the localization of the charge results in stabilization of exa-exa sandwich-like aggregates, right? And of course, no tri or tetra-anionic species because they form exa-exa sandwich-like aggregates. So probably the best solution would be sumanene derivatives, mono or possibly the protonated. And of course, we need to eliminate the influence of the solvent because there is always a competition between target molecules and solvent for metal coordination side. We have performed comprehensive investigation of all possible candidates and came up with the most promising candidate that looks like this, and it has two sumanene mono anions and cesium plus sitting in between. And we asked our collaborators to test whether our ideas is working or it's just, again, pretty much pure theoretical model. Okay, and they came up with a crystal structure of that. And that was the first complete encapsulation of metal center between two curved polyaromatic systems And of course, when you solve their 40 years old problem, it's rewarding. So that's how we got a cover page in Untitled Chapter. But in general, so we were able to just by designing theoretical design of the strategy, how to construct new system, we see that we were able to even solve the problem that was staying around for many, many years. Okay, so before I end up my talk, so I would like to thank to all my colleagues, first of all, my group members, former and current, and of course, our experimental collaborators who are crazy enough to test our ideas. Not all our ideas and suggestions work, definitely, that's a science, but still they want to stay with us and work and test our hypothesis. And of course, I would like to thank all these like IIT and other funding agencies for providing us support over the years. And thank you for your attention.